So before we can start our discussions of this concept that we know is called the mole, this elusive thing called the mole in chemistry, we have to first discuss the building blocks behind it, which are the ideas behind relative and atomic mass. So in the late 1700s, a French scientist named J. Gay-Lussac investigated the gaseous elements that combine to form gaseous compounds. And what he found was that elements always join in a simple whole number ratio by their volume. So when we look at hydrogen and oxygen, as we've got on the left, hydrogen and oxygen always combined in a 2-to-1 ratio in forming their compound. In 1811, Amandio Avogadro, who we'll talk about later and has a very important role in our topic of the mole, explained these results and stated that equal volumes of two gases at the same temperature and pressure contain equal numbers of particles. And several years later, in the 1860s, this statement finally got accepted and became known as Avogadro's hypothesis. This is really important, but it should make a lot of sense because what do we know already about gases? Well, gases actually are mostly empty space. So the fact that hydrogen is very, very small relative to oxygen shouldn't matter as much as how many molecules there are. John Dalton, an English school teacher, took the work of Gay-Lussac and Amandio Avogadro and took it steps further in developing this idea of relative masses for elements. So not only is there a connection between the volumes of gases and the ratios that they react in to form molecules, but also there's a connection between the masses of the gases and the molecules that they form. Relative mass just sounds like the name implies. And anytime you say something is relative, I'm not talking about your uncle or your aunt, I'm talking about a comparison. So anything that is relative means I'm taking something and I'm comparing it to something else. In this particular case, a mass. So by definition, relative mass is a mathematical comparison between objects or an object and an equal number of some other thing. So using other gases as well, Dalton was able to find masses of all gases that he had available to him at the time relative to hydrogen. Since he didn't know the actual mass of each atom of these gas, he assigned hydrogen an arbitrary value of 1 because it's the lightest known element, or was at the time, and it still is, which is fortunate. Now there's a particular advantage to him assigning hydrogen a value of 1, and that is that if every other element is greater in size, then we can think about their masses as being multiples of hydrogen's mass. And multiples of 1 are very easy because it's just the multiple itself. So chlorine has a relative mass of 35.5, meaning that it is 35.5 times heavier than hydrogen. Every other known element at the time was compared to hydrogen. Later, the masses of elements were compared to oxygen. And what I want you to consider is, well, why might that be?
Hindenburg, filled with hydrogen, had been painted with rocket fuel.
There's 15 pounds of thermite on this blimp right now. It's a different sort of beast.
This thing is going to burn.
Thermite's like heavy-duty stuff, and there's an awful lot of it here, so all bets are off.
Test number 3. Thermite megadope plus hydrogen.
It's a safety red alert.
You're lit. Whoa! Dude!
Not surprisingly, the flammable thermite fires up in no time. Add a dash of hydrogen and they're cooking with gas.
Wow!
Now that's a burning blimp. Heinemann's Hindenburg is history.
So why not hydrogen? Well, we know that hydrogen is flammable. If not, we could even almost call it explosive. And oxygen is actually much more available to us. So that's why the comparison was changed and made it relative to oxygen. Today, when we compare elements on the periodic table, masses of atoms are compared to the most common isotope of carbon, carbon-12. We know that carbon-12 has a mass of exactly 12.0. When we look at atomic mass of an element, the ones on the periodic table, the atomic mass of an element is relative to the mass of 1/12 the mass of an atom of carbon-12. 1/12 the mass of carbon-12 is 1. So again, that 1 value is important so that we have multiples of 1 as the mass. The mass of a single atom or element is measured in AMUs, or atomic mass units. Sometimes they're written just with a letter U. What I want you to notice about the masses on the periodic table, as we've already talked about, is that they're not nice whole round numbers. And that's because, as we've already discussed, they are weighted averages of all the isotopes of the elements. So carbon, although we look at one specific isotope of carbon, carbon-12, and it has a mass of 12.0 exactly, carbon as an average of all isotopes of carbon has a mass of 12.01 AMU, the average of all the isotopes. Now when we look at molecular mass is now the mass of a single molecule. And what do we know about a chemical formula? 1, it identifies the type of element in the compound, but 2, it also identifies the number of each element in the compound. So let's look at an example. And we've got copper to acetate. When we look at this, I know that it has the elements copper, carbon, hydrogen, and oxygen. Now I want to look at it and say, well, how many of each of those elements do I have? Because there's no subscript here, I know that there's just 1. Looking at carbon, there's 2 in each acetate, but there's 2 acetates, so that means there's 4. Similarly, 6 hydrogens and 4 oxygens. Again, remember, because the brackets mean groups or multiples of that group, we have to multiply that number to show how many we have in total. Now, if we consider the mass of each element independently, the mass of the molecule is just the sum of its elements. So looking at molybdenum 4 hydroxide, I know that I've got molybdenum, I've got oxygen, and I've got hydrogen. I know that I have just 1 molybdenum, I have 4 oxygens, and I have 4 hydrogens. If I look up the mass of molybdenum in the periodic table, it's 95.94. So that 1 molybdenum is contributing 95.94 atomic mass units to the molecule. Each oxygen weighs 16, so the 4 molecules are contributing 64 atomic mass units to the molecule. And each hydrogen weighs 1.01, so the 4 hydrogen molecule or atoms are contributing 4.04 atomic mass units to the molecule. Adding those up, we see that the molecule as a total weighs 163.98 atomic mass units. So let's look at a couple more of these. I really do encourage you to set them up as I did in the last example until you get very comfortable, and then people will be able to shorthand. But for right now, I encourage you to write down the elements. So this one is magnesium and oxygen. I have 1 magnesium, which is going to weigh 24.31 atomic mass units. I also have 1 oxygen, which weighs 16.00 atomic mass units. So the entire molecule weighs the sum of those, in other words, 40.31 atomic mass units. So now you try with the next example. we have C6H6O6. So we know that there's carbon, hydrogen, and oxygen. There are 6 carbon, which weigh 12.01 each. So that's 72.06 atomic mass units. There are 6 hydrogens, which weigh 1.01 each, 6.06 atomic mass units. And there are 6 oxygens, which weigh 16 each, meaning 96 atomic mass units. Adding those together, we get the atomic mass of the molecule, which is 174.12 atomic mass units. Last one, we look at copper 2 sulfate. Remember, it's copper 2 because the sulfate is a 2 minus, so the copper must be a 2 plus to balance it out. I have 1 copper. I'm going to do it in a shorthand now just to help you to see how you might organize it in a different way, which weighs 63.55 atomic mass units. I have 1 sulfur, which weighs 32.06 atomic mass units, and I have 4 oxygen, which weighs 16 atomic mass units each. So adding those up and multiplying using BEDMAS, so I multiply first and then do the addition. So 63.55 plus 32.06 plus 4 times 16 is 64. I get the atomic mass of 159.61 atomic mass units, or U's. So this is a really quick introduction to relative mass. We're going to build on this very quickly in class and start talking about the actual mole.